This lesson starts the lessons on topic 5.2, or the heating effect of electric currents. In reality, this is actually the start of electric circuits. And so what we're going to talk about today are resistors. So that's basically the topic. As you remember from last year, hopefully, we have resistors, and the primary formula or the primary law that we use with respect to resistors is Ohm's law. We're going to open up and introduce you to many different types of resistors, and we'll look a little bit more into detail about what makes a resistor. First off, the concept of resistivity. Different materials or different substances can be labeled as conductors or insulators, basically based on how easily they permit electric charges to flow. The greater the resistivity, the more a product is an insulator. Okay, the inverse of resistivity, which you may see sometimes, is conductivity. Okay, there is also a third class of materials besides conductors and insulators that is called semiconductors. And these materials can act as conductors or insulators depending on certain conditions. We're not going to go into great detail about how a semiconductor works, but it is important to understand that some of the special resistors that we'll be looking at, as well as transistors and diodes that we'll talk about later, those are made out of semiconductors. In general, materials that are good at conducting are metals like copper and iron. Sometimes you'll see gold. Different examples of insulators are rubber, glass, and air. Basically, the more free electrons a material has, the better a conductor it is. Just as an example, okay, for tables of resistivities, if we look at the top, okay, those are the conductors, okay, silver, copper, and gold, aluminum. On the bottom, and those have resistivities of about order of 10 to the minus 8 ohm meters. That's what resistivity is measured in. On the higher side, in the middle there towards the bottom, we have germanium and silicon. Those are the semiconductors, okay? They're in the order of, -1 to +2 order of magnitude. On the high side, we have things like glass and rubber, which are going to be 10 to the 10 or higher. Those are really high insulators. Notice also that on the third column, there's a temperature coefficient number. And what this number basically says is that materials do change their resistivity with temperature. And that's going to be important, okay? As the temperature increases, most materials' resistivity also increases. Okay, so silver, copper, gold, as the temperature increases, what happens is the molecules start to vibrate more, as we remember from the thermal unit. Their kinetic energy increases. And so what happens is the nucleus of the atom starts to get in the way of the electrons a lot more. It gets harder and harder for the electrons to flow through the material. As an exception to those rules, and this is partially of what makes semiconductors so unique, notice on germanium and silicon, okay, those are negative numbers. So they actually decrease their resistance with temperature. So first of all, let's look at the resistivity of a wire. Okay, if I have a length of wire, the resistance of that is never going to be zero, depending on what the material is made of. Okay, if I have a longer piece of wire, my resistance would increase. And as I increase the width of my wire, the resistance would decrease. Okay, this would be similar to a person walking down a hallway that's full of people. Okay, the longer the hallway is, the more time it would take you to get through it. Okay, similarly, the wider it is, as long as I don't increase the number of people necessarily, then the easier it is for me to traverse it. Okay, so the full formula for resistance is that resistance is equal to this letter P. It's actually the Greek letter rho. Rho is the resistivity that we looked at in the table on the previous slide, times the length of the wire divided by the cross-sectional area. Okay, in the data book, you'll see it in a little bit slightly different format, which says resistivity is equal to the resistance times the area divided by the length. Whichever way works for you. In the past, we've talked about, we've used the formula that I give, which is resistance is equal to rho L over A. People have used the mnemonic that resistance is the People's Liberation Army. So, last year we used zigzags to represent resistors. That's the American format. The IB format uses rectangles to represent resistors. And what we're going to see several different sets of rectangles, and it's important to know the difference. These symbols are in the data book, so if you need to look them up, don't be afraid to use the data book. Okay, first off, over here, we have the standard resistor. Okay, this was the standard zigzag that we had last year. It's just a rectangle. Okay, if we have a resistor that's intended to convert electricity into heat, or basically a heating element, okay, that's going to be represented by these set of multiple smaller rectangles. Okay, then on the left side, we have two different variable value resistors. Okay, a 2-lead resistor is basically a resistor that has that can change its value from 0 to some maximum. Okay, and that's 2 leads. A 3-lead resistor allows you to take out a value somewhere in the middle, and you basically end up with 2 resistors. Okay, you end up with one resistor here that's variable and one resistor here. Okay, another name for this would be a potentiometer. Okay, and then on the right side we have 2 other sensors. Okay, the thermistor is a temperature dependent resistor. It changes its resistance based on temperature, and that way I can use this thermistor to later turn on or turn off some electrical equipment like your air conditioner or your heater. And the last one is a light-dependent resistor. These lines coming in represent light rays. And so a light-dependent resistor is basically the light sensor that turns lights on when it gets dark. So here we have the variable resistors because these will be used most frequently. And basically a variable resistor can change its value from 0 to some maximum. And the potentiometer basically ends up as 2 variable resistors, where this is the center tap. Okay, this is the center of the thing. And it can effectively like move from side to side, changing the value of R1 and R2. However, the combination of those two will always be constant. The temperature-dependent resistor will decrease in resistance as temperature. This is opposite the resistivity we talked about, and that's because thermistors are made out of semiconductors, and so you need to understand that as temperature increases, your resistance will decrease. Same for a light-dependent resistor. As the light level increases, okay, as it gets brighter, my resistance will decrease. Again, light-dependent resistors are made out of semiconductors. Okay, and that brings us to Ohm's law. Okay, we worked a lot with Ohm's law last year, and we're going to expand on our circuit analysis tools. Okay, but Ohm's law basically connects voltage differential. Voltage differential is the difference in voltage from one point to another, current and resistance, and basically the formula that we have for Ohm's law is delta V equals IR. Make sure you keep that delta symbol, okay? I know the data book just gives it in this format, which is R equals V over I, okay? But the delta V is important, okay? Because a lot of times people just take voltage and you just plug a battery into it, the voltage of the battery, and get the wrong answer. Okay, each resistor has its own voltage differential, or another term I'll use is voltage drop. okay, because the voltage drops from point A in this case to point B because my current is going in that direction. Remember, current is going downhill from a higher potential to a lower potential. Current is the flow of positive charges. Yes, it's the electrons that flow in the opposite direction, but we're going to pretend it's the positive charges, and that's what conventional current is about. Okay, so positive charges in this case are flowing from left to right, which means A is a higher voltage than B, and the voltage drop is basically VB minus VA. Okay, so just to reiterate, okay, conventional current is what we will always use. Okay, unless we are specifically asking what direction the electrons are flowing. Anytime we talk about current, it is the conventional current or the flow of positive charges. Okay, so in this case, my current is flowing to the right, so positive charges or positive holes, if you want to think of it that way, are flowing from left to right, from A to B. Okay. If for some reason at times we are calculating delta V in the direction opposite current, okay, and there will be a time that we will do that when we talk about Kirchhoff's laws. Okay, in those instances, delta V will be negative because we are going against the current. Okay, so we talked about Ohm's law, but this law only applies for electronic components which are described as ohmic. Okay, so the only thing about an ohmic element is that the voltage current graph is linear. Okay, there's no curves in it. It's basically just a straight line. Okay, because R is going to be V over I. Okay, and so if R is going to be constant, then V over I, or the slope of V over I, must also be constant. Okay. However, there are many elements that we will encounter that are non-ohmic. Okay. In particular, the IB says that you must understand that this old standard incandescent light bulb, and these are phasing out, so it wouldn't surprise me if IB starts to take this out of their physics as well. But the incandescent light bulb is considered to be non-ohmic. Okay, in this region, yes. Okay, this region is fairly linear, but as I put more and more voltage and current through it, it starts to increase in resistance. The reason it starts to increase in resistance is because it starts to heat up. And as we talked about before, as we increase the temperature of a conductor, and then the resistivity increases and the resistance in turn increases. Okay. On this side, we have the thermistor, the curve for a thermistor. It's a really funky looking curve. You will not be expected to reproduce it. Over here, we'll have something that we'll talk about in a few lessons, and that's the diode. Again, non-ohmic. I cannot use delta V equals IR for these elements. Okay, I could for the filament lamp as long as I'm in that linear portion. Okay. And that brings us to the last formula that we're going to be working with, and that's the electric power formula. Okay, and last year we learned it as power is equal to current I times voltage V, or delta V. Okay, the mnemonic I used last year is P equals IV, or poison ivy. So earlier we defined power as rate of work, okay, the amount of work done per unit time. Okay, and as we moved into electricity, we found out that work is going to equal Q times that change in voltage. Okay, so making some substitutions and then doing some algebraic manipulations, we find that power is going to equal Q over T times the delta V. But current is Q over T, so that's how we end up with the formula that says power is equal to current times change in voltage. Okay, And then when I combine these two formulas, okay, power and Ohm's law, I end up with a couple of other versions of the formula. And that's going to be power is equal to I squared R, if I substitute for V, or V squared over R. These two modifications are also in the data booklet. Okay, so these modifications could be useful and when you're trying to compare two different situations, because if I'm changing the resistance of a material, V and I will both change as a result. Okay, so it's hard to tell what's going to happen to my power. But if I change my resistance, then I can use one of the other formulas because current or voltage may be held constant by some external force. Okay, and so those other formulas might be useful. And we'll see that as we go through some examples later on. Okay, thank you.